Welcome to our AMS Colloquium. Today we have Professor Wang with us, and he's currently in the CS department, and his research interests include data mining and machine learning. So he has been awarded, he has plenty of publications, and he has been awarded the NSF Data Award recently. So today he's going to talk about the learning sparsity-induced models for understanding imaging genetics data.
Okay, thanks for everybody and coming, and thanks for the introduction. It's my great pleasure to give you a brief introduction on my research. So, I'm doing machine learning and data mining. So these are two broadly used and broadly heard sub-areas in computer science. Broadly speaking, they're doing the same. So the both area is trying to analyze data, to identify the patterns from the data, to associate different types of data together. And depending upon the background, depending upon the context we're talking about this type of research, if we emphasize more on algorithm development, then we call this type of research machine learning. If we emphasize more on data manipulation, solve the real-world applications, solve the problems, then we usually call this data mining. But from computer science perspective, we broadly think these are two same things. And both machine learning and data mining has been broadly used in almost everywhere in our life. And as what I did, so I applied machine learning in games, in industrial design, in medicine and medical image computing, as well as surveillance. So machine learning indeed right now, especially in the past few years, when deep learning come to our life, then it is able to solve a number of interesting problems. For example, if you heard just a few days ago, the Turing Prize in 2019 was just announced. It was awarded to the 3 scholars who started to call neural network as deep learning. So deep learning has been there for half centuries or even 1 century. But because it is computation complexity is so big. So in the past 20 years, in 20 years ago, we just simply don't have computers to handle such high volume computation. But due to GPU, due to cloud computing, so deep learning returned back, obviously neural network returned back, and made machine learning hot again. So, but anyway, today I'm not going to talk about deep learning because it is really a big topic. Today I'm going to talk how we can use one type of machine learning to solve the medical image computing problem. Okay, the background of my talk, the motivation to do this research is that in recent medical research, clinical research, we have already confirmed that quite a few major diseases is caused by the genetic reasons, like the cancers, especially like the neurodegenerative disease, like Alzheimer's disease, Parkinson's disease. They're closely related to the genetic variation. So we want to use data mining method. We use a mathematical method to help us to understand how this disease develops and why it appears as this group of people, why they do not appear on that group of people. But directly analyze the medical data and the biological data is not that easy. So we hope to use computers to help us, and this is the motivation. Like for Alzheimer's disease, so right now it is almost confirmed that it is closely related to a small group of genetic units because it's a single nucleotide polymorphism. Instead of to broadly related to a wide spectrum of SNP, indeed it is just only related to a small subset of these SNPs. But as I'm going to show, for human beings, we have around 60 million single nucleotide polymorphism. At this time, if we want to do a full genetic profile for a person, usually it will cost maybe a few $1,000. So everybody, so according to statistics, everybody could have the potential to develop such disease, but somebody could have high potential, somebody may have no risk. So right now, for this type of disease, neurodegenerative disease, especially like Alzheimer's disease, so right now we still call this as irreversible disease. So that means if one person gets it, there is no way to treat it. But the good thing is that if we could detect such type of disease at very early stage, there exists quite a lot of effective physical method to slow down the progression. And also, based upon what I saw in the recent report, for about half of the people whose age is bigger than 60, they just show these symptoms of Alzheimer's disease, just more or less. For old people who is older than 80 years old, everybody show the symptoms. So if we can detect this disease at a very early stage, then we can do something to slow down the progression, to keep our cognition clear. However, as I said, if we do the full profile, then that is too much. Like for me, for myself, if somebody asks me, do I want to spend maybe 5,000 to see how much chance I could develop this disease, then I need to think about it. But if we could use machine learning to identify a small subset of disease that is more likely to develop this disease, maybe just a few bucks, then I don't mind to do it. Yeah, so this is my important motivation. Why do we want to use machine learning? To use data mining to find the association from the genotype to phenotype to clinical assessment and in the end to the clinical diagnosis. So this is the goal. So right now, machine learning and data mining has been used at almost all levels of genetic data analysis. As the smallest unit, we can analyze the single nucleotide polymorphism. So like this is, we usually call this as allele. And also we could analyze at the DNA level, and also we could analyze at the gene expression level. So in my today's talk, I'm only going to focus on SNP, SNP. So this is because at this level, we can see the genetic reason that cause this disease. So the sub-area to connect the medical analysis and machine learning to study this neurodegenerative disease, we call this as imaging genetics. And here I copied one sentence from Wikipedia. So imaging genetics refer to the use of anatomic or physiological imaging technologies as phenotypic assay to evaluate the variations. So we have the genetic data, as I said, as a SNP level, and also we have a big chunk of imaging data in different modalities. And the goal we want to do this analysis is to help us to figure out the reason why and who can develop this neurodegenerative disease. So here for the genotype, we refer to SNP, single nucleotide polymorphism. This is the smallest genetic unit. As I said, for human beings, we have about 60 million. This is a huge number. Obviously, we cannot analyze this by our hand, to examine one by one. But using computers, especially at this time, we have GPU, we have cloud computing, then we can do this very fast and effectively. So this is, as I said, one important reason we want to use machine learning to analyze it. So besides the genetic data, genotype data, we also have the phenotype data. As I said, we have a big bunch of imaging data that assess the participant from different perspectives. For example, we have the diffusion MRI. So this can be used to track the volume change of our brains. And also we have the PET image. This can be used to track the metabolism rate change over some time. And also we have a few different imaging modalities. So this is phenotype, what we can observe from the participant who was involved in our data collection. Then given this genotype and phenotype, what we really want to do is to use them to see how they are related to the cognitive capability of the people. Then we can see, if we see some biomarkers to do some imaging scans, if we see, for example, the volume change of certain area in our brain, then okay, this may be an alert. Then we need to study some training as early as possible. Usually, if we can do the physical training at the age before 50, then it can be very effective if this person could have high risk to develop this disease. Okay, so our goal is to use genotype and phenotype to study how they are associated to clinical capability of the participant. And in the end, we want to see whether the person already has the disease, or they are in the early stage, or okay, this is just a normal control. So the data set we use is obtained from NIH and NSF. About 10 years ago, the government spent a lot of money through NSF and NIH, so they built this platform called ADNI, Alzheimer's Disease Neuroimaging Initiative. They use quite I think I remember is around 30 million US dollar to collect about 1,000 samples. So they invited around 1,000 participants and do the full genetic profile of these people and also collect the imaging record over 3 years. And right now, for the newer version, with more investment, the record can be extended to 5 to 10 years. So this is a very comprehensive data. And the research I am doing, my team is doing, is mainly rely on this data sets. So from the data perspective, we consider the genotype and the phenotype is the input, broadly considered. Of course, in the following research topic, we may not always stay with this. And we consider the clinical assessment and the medical diagnosis as the outputs. So we have input, we have output, then what we want to do is to associate them together to see which marker. So among these 16 million imaging genetic markers, and among this big number of imaging markers, which one or which subgroup of them can show us, okay, this participant may have a high risk to develop the disease. Then, if we have this alert, then we can suggest further clinical assessment, maybe some following training can be done. Okay, so this is the problem we want to solve in imaging genetics. The tools, the mathematical tools we use to solve this problem is to study the association. So depending upon the predictive target, so we have two types of association. So if the output is a predefined discrete set, then we call this a classification. Otherwise, if the measurements, the predictive target are continuous, like the cognitive score, then we call this as regression. So in machine learning, two important tasks is just to do classification and regression. Like classification, we can use naive Bayes, we can use largest regression, we can use neural network. For regression, we can use least square regression, support vector regression, neural network, blah, blah, blah. So we, in our research, first we use existing method to test how good we can estimate the cognitive outcomes and the medical diagnosis using existing tools. Then use this as baseline. We develop our own models, hopefully by utilizing the knowledge we have already obtained from either medical perspective or from biological perspective to help us to improve the estimation, to improve the association. So we associate the input toward the output. This is what this project is doing. Broadly speaking, for most machine learning models, we can construct it by two parts. The first part is to estimate how good our model can associate input toward output with respect to the training data, the ground truth data, if they are available. And besides this, in order to improve the numerical stability as well as to have the better generalization capability, we also have a second term. Sometimes we call this a regularization term to control the complexity of the model, to improve its generalization capability and also improve the numerical stability. So in this project, what we do is just to design appropriate F or design appropriate R so that our model can work stably, and also we can capture the knowledge we can get from the biological domain, genetic domain, and clinical domain. So,
so what are those different notations, like what is W, X, and G?
Oh, okay, yes, sorry. Yeah, so X is input, Y is output.
Y is output.
And the W is the parameter of the model we want to learn.
Oh, that's the parameter.
So we design function F and we design function R. And through this function, together with training data X and Y, we train the model and get the parameters and use for future prediction, generalization for the unseen data.
Where does F come from? How do you choose it?
This is a good question. Indeed, this is a model selection problem. So right now there does not exist a universal way we can solve all the problems. So this is really problem by problem. So what I said, so first we choose the most broadly used learning models. For example, for classification, we can use support vector regression, then this F is just interest. Then we can also use neural network, then this is just a combination of logistic loss, and also other losses. And R we could choose, this is what I'm going to talk in the following slides. So we just use different way to design, to use existing F or design our own new functions. And hopefully we can get a good association with that. Okay, so the main tool we use is the sparsity-induced model. So sparsity indeed is an inherent nature of most real-world data. For example, when we go to see a doctor, if we get some disease, then the doctor at the beginning, he or she may take a lot of medicines, but not all of them are really useful. For example, when we see a doctor, the first thing before we see anybody is they take my weight, take my height, and take my blood pressure. But for some disease, okay, this may be relevant, but for some disease, it may not be relevant. So this indeed just a typical example of sparsity. Then another example of sparsity is that right now we could easily have a huge number of data due to in computer vision due to the very cheap price of the imaging devices. For example, camera. When we have a travel, for example, I go to Washington DC, I go to Paris. Just maybe 3 days, I can take thousands of pictures. But the places I really visited, maybe just a few places. So the inherent pattern is also very sparse. As another example, so for example, when I stay over here and I move over here, okay. So if I use this high-resolution video camera to capture this past 2 seconds, then depending upon this resolution, I could easily use maybe millions of data to describe what I did. But what did I do? I just moved from one dimension. I do not really need millions of dimensions to describe what I did. So this is another example of sparsity. So sparsity exists almost everywhere. So this just motivates us to design a machine learning model so that we can encompass this sparsity and use them to help us to get the expected result. So this is the motivation. And a little bit mathematical interpretation is that, for example, for a specific loss function, if we use the traditional squared L2 regularization, if this is a least square approximation, so this model is also called ridge regression. Then this, by using this regression, we can control the magnitude of W so that it can be more mathematically stable, and also the generalization capability could be better depending on the data. But the thing is that the definition of squared L2 now is just flatly penalize all the terms in these vectors or in this matrix parameters. So this does not introduce the sparsity. So that means although we can flatly to control the overall energy, we minimize it. But we cannot use this model to more explicitly figure out among these maybe 60 million features, then which groups are the most important thing. So instead, we could convert this using the L1 norm regularization. So by this regularization, and if the loss function is least squared, then this is called loss. So because L1 norm can penalize the data somewhat if in an intuitive explanation is just distinguished. So instead of to flatly penalize everything, most of them, if alpha is big enough, then most entries of this parameter will just be either 0 or practically 0. And we can only have a few entries. So this can help us to figure out what are the most relevant. Because if we take a look at this function, if we use the simplest form, least square, so W transpose times X. If a lot of entries are 0, then that means these entries, the corresponding features, corresponding snips are simply useless when we do the association. Yeah.
How about if you use L2 to do threshold solution with L2?
Yes, but the distinction to figure out, so if you can, do a histogram of the L2 parameters, the curve is very smooth. We can do that to select the top ones. But if we use L1, then usually it's something like this. The drop of the magnitude is very significant at a certain stage, so that we can have a better estimation. And also, if we use L2, yes, the magnitude of the element in this vector can be sorted. However, most of them are not 0. So that means they still contribute to the association when we multiply W and X. But if we use L1, okay, even though most of them are not 0, but they're practically 0. So we can simply remove this interest. And from the computation perspective, this can help us to improve the computational efficiency. We do not need to do this calculation in the high dimensional space. Instead, we can do it in lower dimensional space. If the data set is really big, then the computers we have right now can easily handle such estimation and association tasks. So this is also another reason to do the association. And I believe another question may easily come is, since I'm talking about the improving computational efficiency, then why not use dimensionality, for example, PCA, SNP, SNE, all these can do the dimensionality reduction. The thing is that if we use, for example, PCA, although we can reduce the data from a high dimensional space to a lower dimensional space, but the new features is a linear combination of the original features. If we use kernel PCA, then it's even harder to interpret. But if we use a L1 norm regularization, we just select a subset of features. So this does not generate anything new. Just pick up from the original set of observations. So this can help us to easier understand the problem.
What if we pick the wrong features to start with, and it's actually the combinations that do matter?
Yes, this is a good question. That's why we have to do experiments. So right now, what I said is our motivation. Why do we want to do this? Then, and by applying this, then we can analyze the result from the training data. So the training data, that means, okay, we have the observations, and also we know what is the outcomes, and to see whether this model fits. If it confirm that, okay, this works better than the PCA, like the linear combination or nonlinear combination, then we can use this for further seeing data. So indeed, this is a very good question. So basically, why do we want to do machine learning? So why do we have training data? The reason is that we want to generalize from training data to tested data to unseen data. So besides have a good fitting, we also hope it can work for future data. So the training data can help us to confirm the calculus. Okay, so this is the main tool and the iteration we want to use. And here is a little bit mathematical explanation. I believe for this talk, this is not necessary. For some computer science students, I use this figure to explain why L1 norm regularization can produce a sparse result, but the square L2 cannot. But instead of using lasso, this is the simplest sparsely induced model. So we utilize the combination, a mixture of L2 norm and L1 norm regularization, so that we can capture the data structures, particularly for the knowledge we have already known in genetics, in bioinformatics. So instead of use L1 norm regularization or L2 norm regularization separately, we construct a matrix norm so that it can possess some good properties, then by which we can capture the data properties. So here the main motivation to do this is, as I said, so squared L2 norm regularization flatly penalizes all the elements in the parameter matrix. So they, intuitively speaking, so they consider all the elements in the matrix as a whole. Well, the L1 norm regularization consider the elements, involved elements separately. So if we can do a mixture norm, this is the simplest mixture norm. We call it L2 norm. Of course, we can have LPQ norm. So this is the special case of LPQ norm. So 2-1 norm. So for this 2-1 norm, given this parameter matrix W, this D by C matrix, so say we have D observations, 60 millions of SNP, and also we have C number of tasks. For example, we have 100 types of cognitive scores. So this is a matrix. Then instead of flatly either use square L2 or L1, we use square L2 norm, squared L2 norm penalization for every row. And then we use L1 norm across the rows. So as a result, when we use the training data to train the model that is regularized by our 2-1 model, instead of to randomly select a subset of entries if we use a lasso, our 1-1 model, or we just have non-zero numbers for the entire matrix. By using this, either an entire row will be selected, or an entire row will just completely zero. So this can tell us how important, how relevant a feature of, use an example, a SNP, to impact all the cognitive tests. Because usually we don't do just one test. We can, for example, I can give you a paper. I write down 30 words. I give you 30 seconds. Take a look. What word I'm writing. Then after maybe 30 minutes, I ask you how many words do you still remember. So this is one test. Then the other test is that, okay, I can play a music. Then play a set of music. Then after maybe 1 or 2 months, do you still remember what music did I play? So these different types of tests can test a different aspect of a cognitive test. So if we use lasso or use the ridge regression, then it's hard to figure out how measure impact everything. But this 2-1 now can do this.
So, people have been using elastic net.
Okay.
The combination of L1 and L2.
Yes.
So, why do you pick elastic net and why do you choose to pick this particular connect?
Yes. So for elastic net, so what we do is to Frobenius norm square plus this W 1-in-1 norm. So this is elastic net. So the reason why we want to do this, so if we use 1-1 norm, then the sparsity can be introduced. However, usually 1-1 norm, because it is not smooth. So when we do the optimization, particularly go to the later stage of the iteration, the algorithm will become very unstable. So as a result, we can further use the ridge regression by combining the square of Frobenius norm, so that this is very stable. This is then by combining this, so the algorithm, we can get sparse solution, and meanwhile the algorithm is very hard to be unstable. So this is why we want to use elastic net. However, as you can see, we use L2 norm, square L2 norm, and L1 norm separate. So this can be written as L2 norm square Wi sum over I. So this is just sum over Ij, Wij was the absolute line. So for either case, you cannot capture the structure. So as I'm going to show in the following slides, we want to utilize this combined L2 norm and L1 norm so that we can utilize some information, for example, the grouping information. Although, as I said, we have 60 millions of single nucleotide polymorphisms, but they're not working independently. Instead, they work as groups. And this grouping information can be captured using appropriately designed mixture model. But of course, this is the simplest mixture model.
So in your case, you only have one regularization parameter.
Yes, we could have many. So this is trying to capture the structure. It is sometimes we also have this term, Frobenius square, to improve the stability. But this is the main part to drive the structure of data.
It's complicated to determine the regularization parameter.
Yes, exactly right. So this is what I usually said in my machine learning class. Not free much. If you want to achieve this, you must pay something. Yes. So you're right. Yes, this inevitably complicated model. But the good thing is that we have less people, right? So we can solve this more complicated problem without incurring too much computational cost. Okay, so this is the main motivation. We want to build a mixture sparsely induced model so as to do a better association. Okay, so I'm going to use a few tasks to show how we can use sparsely induced model so as to solve the problem. So this is a diagram, the roadmap of my current project to do the medical imaging analysis. So we analyze the data from the task perspective, so basically from the outcome perspective. We can also design the model from the input data perspective. And as I mentioned, so sometimes we also have some special grouping information, special data structure information. Then we can use this this mixture norm regularization to capture this. All this, the first upper two block to deal with the data at the static time. So we study the data at every single time point. But the thing is that neurodegenerative disease, it is a progression of the impairment of our cognition capability. So if we study the observations and outcomes separately at different times, it is fine, it can provide with a lot of insight. But if we could use all the data together, so to study the time series data and also utilize the same models, then hopefully we can get some more insight. So this is the roadmap of the project which I'm doing. Okay, so just now I have introduced the background and the main motivations. So in the following talk, I'm going to introduce these 5 different tasks and how I use this structure imbecity to solve the problems. Okay, so first one starts from the simplest case. So when we study the homogeneous task. So the homogeneous task, what we do is to use the phenotypes, use a different type of the imaging modality data to associate, to predict what will be the cognitive assessment outcomes. As I said, cognitive scores, although we have quite a few different type of tests, like about 100 different assessment tasks, but most of them are designed as a continuous predictive target. So the most straightforward way is to design a regression model. But in this part, what we mainly focus on is how to use the sparsity regularization to improve our understanding with respect to regression model. So here, if you still recall the formulation I write over here, so we have F function and the R function. So in this task, we do not care what F function we use. Instead, we can try to use not traditionally used R function to capture the knowledge we have. So okay, so this is the data we use. So we use phenotype as input. This is X matrix, and also we have a number of different cognitive tests. So every row over here, so this is a Y transpose. So every row over here is just a different cognitive test. For example, how many words you can remember after some time, and how many music songs you can still remember after a few months. And here the columns, and similarly the columns over here, are just different participants. As I said, we use the ADNI data set. In the first version, we have about 800 samples. Even though it's not very big, it spent around $30 billion. Very expensive. And in the newer version, we have around, I don't remember, how many samples do we have? 1,000 something, right? Yeah, so we have a newer version. So right now we move from older version to a newer version. Okay, anyway, so this is the data we can analyze.
Your input, I don't understand the roles. So you labeled the image 1 to image 90. How do you assign integers to images?
Oh, so once we get these brain scans, we will work with our collaborators in the medical school. They will do the translation. So instead of to use these raw pictures, the brain regions will be split into a number of regions. So like for MRI, we have around 80 regions. So that means we have 80 rows if we want to study the volume change of the brain. And also for the PET image, we translated into around 90 different regions.
So that means you're using one type of image and just assigning
different regions of the brain. Yes. So we cannot do this by ourselves. We have to get these numbers together with our medical collaborators from medical schools. But what we do is after this data has been pre-processed, then we use machine learning model or use the statistical model to study the association. Okay. So the first thing we do is largely an extension of elastic net. So R21 now, here we have M function, so this just tells us the fidelity of our association. So we can use the simplest one. So this is just a linear association, but of course we can use kernelized version, and we can use support vector regression, we can even use neural network if we do have a lot of computation results. But we can use this simplest one to do the illustration. So as I said, we want to identify, as I said, we have 60 million SMP. If we want to do the full profile, it costs us thousands of dollars for everyone. But not every SMP is really relevant to the data. As far as I know, for after 20 years of studying Alzheimer's disease, there only exists about less than 1,000 SNPs that really developed the data. So if we do only around this subgroup, as I said, the cost is just a few bucks. So this is a problem. I don't mind to do that, as I said. So we want to use L21 now, which I showed in the previous picture. So we can either select the entire row. So we can see that the row over here is the imaging features, so different regions of our brains. And the columns over here are all the tasks we have performed. Then if we can figure out which features, then we can, instead of to do the full profile, genetic profile, let's just do this small group. And also, if we do the brain scan over the entire brain, this is also very costly. I cannot give you a number, but obviously, let's just do a small region. So for the entire brain, we can translate it into around 80 different regions. But if we just do a few mainly hippocampus, then this is one of the most significant indicator of the development of Alzheimer's disease. If we see the significant shrinkage of hippocampus, then okay, this person really needs to do some further clinical assessment. So using this analysis, we do not have to do the brain scan over the entire domain. We do not have to do the genetic profile over the entire spectrum. So here we use the 2-1. And
But is it reasonable to assume the linear dependence on W for the fit?
what's the question again?
X transpose W, is that reasonable as a linear dependence on W?
As I said, in this task, we mainly focus on these two parts. If we believe there do exist nonlinear things, we can either kernelize this one, or let's just maybe use objective regression, or using neural network. Then the nonlinear relation can be captured. So we have done the experiment using the simplest linear fidelity test, as well as kernelized version and also SPR. And we do see that the selected features, either in brain imaging, so that means the region that can use that indicator from phenotype, they remain largely stable. And same for the genetic indicators. Okay, so this is the first thing. Now, of course, to solving this problem is a little bit harder than solving the ridge regression that we can just solve by one shot. Because these two terms, regularization term, are not smooth. So we will have to use a little bit more complicated optimization method. And what we do is use a majorization. Or in our domain, in machine learning domain, we call this iterative weighted method. So basically, we convert this non-smooth problem into a smooth problem. But instead of to use the original regularization, so every term can be written as so. Basically, if we have this 2-1 norm, then we can write it as a trace of the transpose. So this is smooth at every iteration. Then we can use this on it. And this D is the L2 norm of every row of this matrix. So, oops. Okay, so we use this majorization method to solve this problem. And the advantage to use majorization is that it's very fast. It converges just by a few iterations. The disadvantage is that it cannot go to very, very good objective value. Once it go down, the objective go down to a certain level, it will just stay there, but it may not be very good. So right now we are also starting to use other optimization methods. For example, we use augmented Lagrange multiplier method to solve the problems. So this is still ongoing, but the main motivation is that using this structure sparsity, so we can figure out what are the most relevant parts. So this is the simplest model, simplest task. Then we can generalize a similar idea to solve the more complicated problem. So instead of to study the same type of predictive target, we can study the different types of predictive target together. So basically, we know that from the figure. So cognitive capability indeed determines the diagnosis test. So instead of to do the prediction of the cognitive test and the diagnosis separately, we can do them together. And this is an illustration why this could be beneficial. So in traditional clinical practice, if we have some symptom, then the doctors will associate to some continuous quantitative trait, and then use this quantitative trait to associate to the genetic cause. So if we have this disease symptoms, then because this disease is related to QT1 and QT2, and for QT2 is related to 2 genes, but indeed only one of them is a real cause. So if you use this multiple stage analysis, sometimes we can get some result which may not be correct. But if we study the diagnosis, so basically these two stage of task at the same time, and couple them using this structured sparsity, then hopefully we can have a better result so that we can know, okay, gene 3 is just related to the normal control and not related to disease. So this is the motivation. And the data we will use is still use the phenotype data, and for the output part, we will associate the phenotype to both the continuous cognitive test as well as the discrete diagnosis result. So we have two laws over here. So instead of just have one function, so we use two fidelity test function, L1 and L2. L1 can be used to test the regression performance, and L2 can be used to test the classification test. Again, what L1 and L2 are is not a big problem. So the main goal is to couple them together and use this L2 one. So in our experiment, in order to have a better probabilistic interpretation, so for the classification part, we use a Lorenz regression. This is most doctors, physicians, they like this. When we have this outcome prediction, we can also tell okay, how confident we are. So instead of like small vector machine, it is very good in terms of do the prediction, but it's not that easy to interpret, not mention neural network, that is even more complicated. So for a better interpretation, so for the classification part, we use Lorenz regression, but of course we generalize from the binary Lorenz regression to a multi-class Lorenz regression. And for the regression part, once again, in order to have a better interpretation, we still choose the simplest least square estimation. And again, solve the problem, we'll have to use the non-smooth optimization solvers.
Is there a reason you have some sort of parameter controlling the trade-off between your L1 and L2? Not the regular answer, but yeah.
Okay, yeah. Yeah, so for the first model, we learn W, and for the second model, we learn P. Both of them are parameters. Then we combine them together and use L2 one now so that it can go through both regression and classification. So for this term, besides it can capture the relevance across all the both classification and regression terms, it also serves as a magnitude control. So you can see that, so this is, well, we just minimize this objective. So if we give this gamma a bigger value, then the magnitude of the parameters W and P will be somewhat controlled.
Well, then that should control the magnitude of privilege, but not necessarily the trade-off between how much you care about regression being good versus classification.
Yes. If we really want to do it, as I said, we could add one additional forbidden square just over W and a forbidden square just for P, so that we can control them separately or emphasize them separately. The main reason I write this formulation over here is to keep it as simple as possible, so that I can highlight I use 2-1 norm. So 2-1 norm can go across the both type of classes. But this is, as I said, lasso is very good, very simple, very easy to understand. But in practice, we do not use lasso directly a lot. Instead, we use elastic net because lasso is not very stable. So this is same over here. Okay. Again, because here we use the 2-1 norm, so solving this problem, I have to use non-smooth optimizer. So we again use the majorization method. And the result is reasonably good, and we can see for the classification part, we can improve. This is classification. Compared to use the support vector machine, just do the classification task separately. By using this combined regression and classification, the result is improved. And similar for the regression. If we do the regression separately, then the result is not as good as when we do this multi-stage regression classification together. And the most important thing is, this can help us identify the biomarkers that really develop the disease. So you can see that this is a learned parameter V, so it's a combination of W and P. So we can see either entire column, but this is a transpose of the matrix. So either the entire row is selected or entire row is simply discarded. So we can see that like this hippocampus. From the clinical record, this has already almost confirmed that this is the most significant indicator of the development of the Alzheimer's disease. If we see the shrinkage of hippocampus that is over here, then this people may really see the doctor as soon as possible. And similar for this is the external party. This is another clinical indicator. So all these result perfectly in accordance with clinical findings.
ABC, these three charts.
Oh, these are different types of regression tests. Cognitive tests. We have tested on 3 different groups of cognitive tests. So this is called MMSE. This may test wording. This is RAVLT. This test is understanding of a longer paragraph of text. And this is trails. This is the sound.
Hippocampus doesn't matter for some.
It looks like, yeah. So we are still talking with our medical collaborators to see what is happening. Yeah, but at least for this tool, yes, it is true. Okay, so this is the analysis from the output perspective. We also have performed analysis from the input to design a regularization term so that we can capture the additional information from the input perspective. So, as we said, genetic information is a fundamental root cause. So genotype lead to phenotype. Then, by using phenotype analysis, we can do the diagnosis. So in this study, we study how genotype observations is related to the phenotype. But different from the traditional, using the traditional regression models like the least square, like the smart vector regression, like neural network, here we observe that although we have 60 million SMP, but the number of genes we have is just 8,000. And particularly for the genes that's related to the development of Alzheimer's disease, only 34. So we have these 34 genes. So we group using this, and this every gene contains a number of different SNPs. For example, this gene has around 400 SNPs. So instead of to study the association flatly penalize all the features, we can further utilize structure. So besides this natural, the chemical grouping structure, we also have some clinical correlation called linkage similarity. So not every pair of SNPs are related to each other in the same way. So for the SNPs we studied, this is the patterns, how they are similar, how they are connected to each other. So this gives us another way to do the grouping. So here we design a new norm called group 2-1 norm. So again, it is a combination of squared L2 norm and L1 norm over a matrix. But instead of to define it over a single row, we can define the squared L2 norm of several rows if these SNPs are from the same gene or they are closely related to each other. So that means when we do the penalization, we will penalize all these entries as a whole because they are related. When they work, they should work together. When they don't work, all of them will not work. So we introduce the L2 norm over these several rows, and for every block, we impose L1 norm. So we can easily prove this satisfies all the criteria to be a norm. Then we use, once again, we do the regression analysis. So here we have this group 2-1 norm to capture the clinical or genetic grouping structure. And meanwhile, we can also use a 2-1 norm so that we can figure out how each individual markers develop the disease. And then we develop optimization algorithm. Once again, we can use visualization because it is very easy to implement. And the result is pretty encouraging. So by using this grouping 2-1 norm and compare it to not using it, by either just use square L2 norm, like ridge regression, or we can use 2-1 norm to do the regularization. By using them together, we can see that the result is better. Either using the group by genes, this is chemically meaningful. However, from the clinical perspective, it may not be as meaningful as grouping using the linkage affinity. But for either case, it is better than just simply use the ridge regression. So this again confirms us to using sparsity to capture some data structure, it can be useful. And here we analyze how the genetic SNP hits to across all the participants, and we can see that this one has the biggest number of hits. So that means this appear in most participants. Again, this is employee. We have already seen a quite large number, more than 2,000 of published papers that confirm that this SNP really developed. But in this 2,000 papers, they have to use very costly chemical, biological experiments. What we do is just use computers to do the simulation. Okay, so this is the first task from input perspective. Then the next task is that the input indeed include two different things, either the genotype or phenotype. And for phenotype, we have MRI image, we have PET image, we have CT image. All of them are different. They tell us how our brain are working from different perspectives. So we can consider them flattening. But if we can use structured sparsity, then we can do the prediction in a better way. And this is how we do it. So the input will be the input from both genotype and multiple phenotype. And what we do is to introduce a group 1 now. So we can see that for every modality, for example, this the measurement from the genetic. This is a group from one imaging modality. Within this modality, we use square L2, so that all these measurements are considered as a whole. Then across different modality, we introduce L1 now, so that they will be selectively penalized. And this can help us to have a better understanding when we use as much data as possible. In the previous analysis, we only studied one modality toward one group of prediction target. But here, we can study all the data together. And this is the objective. Again, for the fidelity part, we do not use very complicated things for interpretation. Of course, we can use a more sophisticated one for better performance. And this is objective we want to minimize, and this is the algorithm we developed. Again, it's fundamentally derived using visualization. It's very computationally efficient. And this is the result. If we study the prediction by every modality separately, so this is for regression, this is for, this is for classification for every modality separately. This is to use the traditional fusion method. For example, we can use multiple kernel support vector regression. But the thing is that they will penalize the entire modality data as a whole. But they cannot consider one features as incorporate every features. So for example, maybe this type of features observation is wrong, but this does not mean all the observations within this type. But traditional multiple kernel support vector machine can only do penalization over an entire modality. But our model, as I showed in this figure, besides penalize through every modality, we can also penalize over a single feature. So as a result, we expect this method can, our method is better. So indeed, it is better. Okay, so this is the selected markers. So you can see that hippocampus again is selected, and also this one. This is the inferior part of the temporal. It is at the front of the brain. It is also another very important biomarker that indicates Alzheimer's disease. Okay, so this is how we use the sparsity inducing to fuse multi-modality data. And finally, the last thing is to study the data over time. So this is fundamentally the same as what I showed in the previous 4 projects. The only thing is that we will study this over the entire trajectory. So if we use the summarized value, for example, using this one, either the starting value or ending value or the average is pretty high. But if we study over trajectory, then this blue and the red things are very different. So here we define this model. And we define the last part still use the least square approximation, but of course because of the temporal change, so this become a matrix approximation into a tensor regression. And we, instead of to do the regularization over all the elements in the tensor, we will design the regularization to go across every row after we unfold the tensor from different mode. For example, when we unfold the tensor from the temporal mode, then that means this feature will go across the entire course of the disease development. If we unfold it along the task, the predicted outcome mode, then the observed feature will tell us how relevant this observation impacts all types of cognitive probability and disease. So this is a model we propose. So basically, it is just a tensor version of least square regression and the tensor version mixture now. But obviously, it is more complicated to solve, but the good thing is that miniaturization can help us to solve this problem in a computationally efficient way. And this is the algorithm. Again, this is the performance, and we can see using ours, the correlation between the input and output shows the highest correlation. And the temporal change over here, so the markers over time and markers over task. Again, we can easily find a lot of clinical findings to confirm the correctness of our statistical findings. Okay, so this is just another type of interpretation. Okay, to summarize, so we use structured sparsity to solve the regression and classification over this AD data from different ways. This is a roadmap, and this project is still ongoing, and it is supported by my NSF career grants. Hopefully we can have some more significant results in the next couple of years. So this is my team. I have 4 PhD students, I'm sitting over there. And also I have 3 master graduate students, and usually I have 5 to 10 undergraduate students in my team. So if we have undergraduate students over here, and if you're interested in doing some research, please talk with me. My team is called Machine Learning, Informatics, and Data Science, MIND otherwise. Okay, so this is all I have. I really appreciate you sitting here. If you have any questions, I'm more than happy to answer.
Jeff?
So, earlier when you first started talking about the optimization, you were saying it's going to cost presumably a local minimum.
If you can take a look, all these objectives as I show over here, as long as the loss function is convex, then the objective is convex. So if in the end it will go to global optima. So like this one.
That's what I was going to say. I was confused then why you were saying that it kept getting stuck.
Oh no, it's not getting stuck. It's not getting stuck. It's because this norms is non-smooth. So it easily causes a numerical instability problem. So the results can oscillate over the solution here and there. So it's difficult to control.
Isn't that what the second term is? The second?
Yes, this term is, you can see that over the D dimension here, it's L1 norm. So it is non-smooth. So this is particularly important when we deal with high dimensional data. So we have multiple non-smoothing points in the space.
But isn't that what the ridge term that you're using is supposed to control? Your camera.
You mean this
I
one?
don't see it in the other.
Huh?
I guess I don't see it here, but in your previous
Previous one?
answers.
Okay. So all these objectives are convex. If the loss function is convex.
But your gamma 2 term, isn't that going to control?
Oh no. If we want to improve the numerical stability, we will have to use Frobenius square. I did not show it on my slide in order to make it simple. In practice, we do have that. That can help us to make it more stable. Here, I want to emphasize this newly introduced. This is not like what we traditionally do, use L1 norm or square L2 norm. This is a mixture norm. So in structure, it has both square L2 and L1. So they have their specific meaning with respect to the data.
Your accuracy results, can you go to the slide where you show the results for accuracy? It's like 2 slides further. Yeah, so it's overall pretty low, right? So it sounds like there's a lot of things. What do these numbers actually mean?
Yes. This depending upon how we interpret low. Yeah, because if we just no. As I said, in this research, important reason is to identify a subset of biomarkers so that we can reduce the cost to the diagnosis. If I really want this number high, I can use a more sophisticated loss function. So, but in all my slides until so far over here, for the loss function, I use as the simplest. If I really want to fit the training data, I can use a neural network. That's why Turing Prize was awarded to deep learning guys this year. I can easily get very high numbers. But the thing is that by using that, how to interpret the data will become more difficult.
Okay, so but I guess my larger question is, are there a lot of factors that are not explained through genetics that contribute to early Alzheimer's disease that are not captured by genetics, like lifestyle or other things that would seem pretty reasonable?
Yes, indeed, this is part of our study when we want to study this time series data, so that hopefully we can find some different discoveries from when we study from the static time point association separate.
Okay, but that brings back to my second question. Yeah, that's like, so we would probably, you're still using these data as discrete inputs, versus in statistics, we would probably think about this as functional data and try to use that information, which is a different way of thinking about it. You would think about this data here as a function rather than individual data points. So
yes.
That might be a different approach to tackle this.
We are thinking this, but here, as you see, we just use a regression. So basically, we have this inputs at different time and also output have the same time, but we want to study over the entire course. So this is what this study is doing. Your question, of course, if we consider this as a function and then our model is functional, then this is something we could do in the future. But right now, we have not yet done that.
Most of the references I saw along the way were from 2011, 2012.
Yes.
So what are you doing today?
What I'm doing today is to is to develop a better optimization algorithm and better loss function part, as well as more complicated regularization. So indeed, like Loki is my student. We just have a paper in last year, MICA. That is the best conference for medical image computing. It's just study how we can combine the fourth and the fifth task together. So here in my slide just now, I do this separately. What he did in the last year is to combine this together, which produced very good results compared to this. We do this separately.
Any further questions? All right. So let's thank our speaker one more time.